Right, so the recording is on. This is SQL Friday number 122, and Hugo is back. And I mean, Hugo is back on SQL Friday, but Hugo is also back to some in-person presentations, which at least I'm extremely happy about. I haven't had the chance to see you in person yet because we haven't gone to the same events, but that will happen sooner or later. Uh, Glad you're doing well. Glad to have you back. And today, Hugo will talk about advanced indexing. So, beyond knowing that you should have a primary key and you should have a clustered index that is fulfills the news properties and so on and so on. When the things you always do isn't quite enough for your performance, what should you think about? Is that a good summary of what you will be talking about?
Yeah, kind of. I also have a conference tool called Indexing Basics, where I basically explain the structure and the access methods of clustered, non-clustered, and heap indexes. Well, not heap indexes, clustered and non-clustered indexes and heaps.
Yep.
And this takes it one level up. It's called advanced indexing, but it's not a very deep level. It's still pretty easy to access, I hope.
Yeah, nice. I mean, you can go with indexing if you want to do advanced indexing. That could be 1, 2, 3, 4 week course. So
Yeah, easy.
in an hour, you only manage this much.
Exactly. And
But
that's exactly the idea.
the stage is yours, and I'll just relay questions from the chat if there are any.
Yes,
Uh,
please do. And I
and
won't need to keep my eye on the chat and I can focus on presenting. Just interrupt me when there are questions.
I will do. Good to have you here.
Thanks for having me and welcome everyone. Glad to see you in my session on advanced indexing. My name is Hugo Kornelis and I make SQLServerFast.com. SQLServerFast.com is the website that I created when I decided there needs to be better documentation for execution plans. We will see execution plans today. A session from me without execution plans is a rarity, but they are not the key focus. But I very often talk about execution plans, and I love execution plans because they give such great insight in what went right and what went wrong with the performance of queries in SQL Server. They are a fantastic tool. The only thing really missing is good documentation, or rather, the only thing really missing was good documentation because when Microsoft didn't make it available, I decided to do it myself. And that's when I started the execution plan reference, which, as the name says, is a reference. You can find almost everything you want to know and a lot of things you don't want to know about execution plans on that website, but it is in a very reference method description. So it's not easy accessible. It's not teaching material. People asked me to make that available as well. So I started working a few years back on the execution plan video training, which has basic and advanced levels, where I take everyone who is interested from complete beginner to almost expert. The only thing missing that I cannot provide is actual experience. And that is actually intended to be training material on execution plans. Some of them are available for free. Some of them are sold. Um, because I always want to give something back to people who give their time to attend my sessions, I am going to give all of you a 10% discount using the code SQL FRI, and watch the capitalization, short for SQL Friday, of course, which is valid until the end of the month. Now, if you are immediately going to go there, that's not smart because in a few days, during the entire month of November, there will be a Black Friday sales of my videos, which gives 50% discount, and this code works on top of that. So wait a few days and then use this offer to get an additional 10% off the already 50% discounted prices for my video training. I also have on sqlserverfiles.com my blog. I have articles, and the most important thing for now is the resources section where you can find the slide deck and demo code for all my sessions. So if you are interested in seeing the slide deck or playing with the demo code, just go to my website, go to the menu choice Other, then Presentations, then Presentation Resources. That's the menu options. Then you see a list of all my conference sessions. Click on this one, Advanced Indexing, and you will find a download link for a zip file with slide deck and demo code. I do a lot of other stuff as well. Nobody cares about who I am and what I do. The only thing that's really important about me is where to reach me. So if you have questions now, type them in the chat and Magnus will read them to me. If you have questions later after this session is over, please send me an email or hit me on Twitter, X, I should say now. I try to always respond to all mails. If you mail me and I don't respond within a week or so, then I probably have overlooked your email. Don't get mad at me. Just send me a gentle reminder and I will get back to you. Things we are going to talk about today. We are going to talk about included columns in indexes. We are going to talk about filtered indexes. We are going to talk about indexed views. We're going to spare a few words on finding the right indexes. And then I will show you the danger of over-indexing, because more indexes is not always better. We are not going to talk about index maintenance, not because index maintenance is unimportant. It is very important, but I have to make my selection of what I can cover in an hour, and I decided to stick to the mostly development performance side of things and not on daily maintenance. That's important, but I don't have time for it. And new is between parentheses, between apostrophes right now, because those index types aren't that new anymore. Column store indexes were introduced in SQL Server 2012, memory optimized in 2014, I think. So they're not exactly new index types, but they are still relatively less used than the regular on-disk row store indexes. And simply scoping of the session, I do not have time to talk about those indexes. I also will not talk about the specialized index types such as XML indexes, free text indexes, and spatial indexes. That leaves us with the topics that we are going to talk about, and we are going to start with included columns. Included columns are one possible solution to a problem caused by the index seek plus key lookup pattern. So what sometimes happens if you have a query is that SQL Server finds an index that it can use to quickly find the correct rows, but within that non-clustered index, not all information is available. So it then has to reach out to the clustered index to find the additional information. And that is where the key lookup comes in. So if you look on the screen, you will see a very simplified representation of a non-clustered index that is indexed on the combination last name, first name. And we have a query where we want to find information for everyone with last name Visser. But the information we want to return is more than just last name, first name, and a person ID, the clustered index key. We also need to find additional information from the clustered index. That was one click too fast. So what SQL Server does is it starts using the very efficient seek pattern to quickly find the first person with last name Visser in the non-clustered index. That's Annette Visser with person ID 81. But we need additional information, and that's where the clustered index comes in, which is now represented on the right. In the clustered index, this person ID 81 can be used to also very efficiently navigate directly to person 81. And there we can find the other information in the other columns that is also stored on that leaf page. So far, it's very efficient, but we want all persons named Fisher. So the seek on the non-clustered index on the left continues. It goes to the next page, and there we find another person named Fisher, Klaas Fisher. He has person ID 3, which results in yet another efficient, but still another lookup in the clustered index. And at that point, when we read on in the non-clustered index, the next person has a last name which is alphabetically past Visser. So we know that we have returned all the data. So with just two people named Visser in this example, we had one index seek plus partial scan of the non-clustered index, which is as efficient as it gets, and two lookups in the clustered index, each of them requiring, in this example, 3 logical IOs. And in the worst case, some of them might be physical IOs. Now, 2 of those 3 logical IO seeks is not that bad, but what if there were a million people named Fisher? Then all those key lookups would add up and you would get 3 million logical IOs. And some of them might be physical IOs. Then it gets expensive. And that's where the index seek plus key lookup has this tipping point where it is great for a few number of rows, but terrible for a large number of rows, which means that you can get bad performance if SQL Server gives you an execution plan with this pattern, because it thinks the number of rows will be low, but then the number of rows is much higher and you get bad performance. Or you get bad performance because SQL Server thinks the number of rows that matches will be too high. I am not even going to use an index seek plus key lookup. I'm just going to scan an index. So, as I explained, this pattern happens when a non-clustered index. Oh no, sorry, step back. This was what I was going to say is the covering index. The covering index is, there is a misunderstanding with this term. Sometimes I hear people talk about, is this a covering index, or this is a covering index? And that is a statement that doesn't make sense. An index can cover a query or multiple queries. And it might not cover some other queries. An index covers a query if all the data needed for the query from that table is included in that index. So to determine whether a non-clustered index is covering or not, you need to know what data is in a non-clustered index. Of course, the indexed columns are in the non-clustered index because we search on those columns. There's also all the columns from the clustered index are also included in all non-clustered indexes because that is required to be able to find the rest of the data. And then, optionally, we can include extra columns in the leaf pages only. So we give additional information that we put in the index, not to enable more searching, it's only in the leaf pages, but to enable the index to be covering. So here is once more the non-clustered index I showed in the previous slide, an index on last name, first name, with a reference to the clustered index on person ID. If we want to include an extra column, for instance, the mail column, then the mail address will be added on the leaf pages, as you just saw when I clicked my clicker. Except, of course, putting extra information on leaf pages doesn't always fit. In reality, this takes up extra space, so now we have less rows per leaf page. So the reality will be more like, oh, we now have more leaf pages. And that is the price of the included column. The benefit will be that if we need the mail address in our query, we now no longer need this key lookup, and we get much better performance. But other queries that don't need the mail address also will have to read those leaf pages with the mail address. So other queries might get worse performance because of this. That may not be a lot, but it is still there and you need to be aware of it. And it will be a lot if you include a lot of columns. So always be smart about which columns and how many columns, most of all, you include. Don't overdo it. Now, if you want to create an index with included columns, you have to create a new index. There is no alter index syntax that allows you to add or remove included columns. So if you have an existing index and you want to add an additional included columns to make it covering for an important query, then you will have to drop and recreate the index. Included columns can only be used on non-clustered indexes, and that makes sense because clustered indexes by definition already include all columns in the table, so you cannot include additional data. There's no restriction on the number or the size of the columns, except that the data types text and image are not supported as included columns. But frankly, if 18 years after these data types were deprecated, you still use them in your systems, you probably have bigger issues than a covering index can solve. Here is the syntax. You used a regular syntax to create a non-clustered index, and then you add the keyword include and then a comma separated list of columns, and all those columns will be added to the leaf pages. Let's look at a demo of this. So I already created a demo database, and let's see if I can find my mouse. There's my mouse. In the code, I'm not going to look at all the code, but what I do at the end is constantly copying all the data from a table into itself to double the size of the data. At the end, I have almost 1.3 million rows in the persons tables. And that's all I do. I already ran that before we started. Let's now look at an example. So I'm going to look for persons where the last name starts with an S or starts with a V. Because I use like, this can be done with a seek. If I run this with execution plan with runtime statistics enabled, you will see that the results come back. And in the execution plans, you will see that one execution plan uses a clustered index scan, and the other execution plan uses this index seek plus key lookup pattern. The reason for this difference is that this second execution plan has an estimate of about 13,500 rows, and that estimate is almost correct, whereas the other query has a much higher estimate of 10 times as much rows. And with 10 times as many rows, the number of lookups would become very expensive. If I look at the statistics IO, you will see that the first query did 57,000 logical reads, the second did 42,000 logical reads. If we had used the index seek plus lookup pattern for the first query as well, this would have been almost 10 times as much, 420,000 logical reads. So the optimizer made the right choices here. But it had to choose between a rock and a hard place because there was no ideal way. There was no covering index that it could use here. And that's where this syntax comes in. The index that was used, I forgot to say that, the index that was used here for the index seek is an index on last name and first name. The definition is not visible here, only the name, but if you go back to the setup script, you will see that this is an index on last name, comma, first name. So it can be used to find on last name only or on the combination of last name plus first name. Basically the index I had in my slide. I am now going to create a new index on last name only and include the first name and email columns. So I'm going to include both first name and email because they are both needed in the query and will not be created in this index. So I need to include them so that they are all there and the index covers this query. So let's create this index and now run the same queries again. And now you will see in the execution plan that they both use an index seek. The estimates are still a factor 10 apart, but they both do a seek on this new index that I just created. IX person name include. The second one also seeks this same object, IX person name include. So we can now use this seek to efficiently find all the rows that we need, whether it's 13,500 or 135,000. But we get a much better performance with only 969 or 103 logical reads. So for this specific query, we saved a lot of performance. Now, I don't want to create specific indexes for each and every query. So in this case, I already had an index on last name plus first name, and we only needed an index on last name here, but I realize, what if I drop this index I just created, and instead, so here is how I had it first. Index on last name include first name and email. Instead, I do an index on last name and first name and include email. If I use this, create this index, then this index can also be used by queries that use the already existing index on last name and first name without included columns. So I should now drop that index too. I do not have that in the demo, but if I do this on a production system or on the development system as a preparation for later deployment to production, then I would drop the index on last name, first name without included columns as well, because I don't want overlapping indexes. Now these queries become slightly less efficient because I added the first name as an indexed column, but they are still very efficient. As you see, the number of logical reads is up by, I think, 1 for the first query and unchanged for the second query. That's typically the amount of difference I see. It's not always exactly the same if I rerun this demo, but it's usually these numbers. So there is a slight overhead to putting first name as an indexed column, but the benefit is that you can now safely drop that other index that was used at first. And that is, of course, a huge saving. Are there questions on included columns?
Nothing in the chat. There were some conversations about a person named Hugo K, who wrote an excellent Stairway article series on SQL Server Central about.
I think I know that man.
Yeah,
you shouldn't trust him. You shouldn't trust him. No,
I want to include
that is correct.
To Nico's articles, but his website is down, so I couldn't. But,
my idea when I wrote that Stairway was to provide a bridge between the very basic coverage that was available back then in Microsoft's documentation on column store indexes and extremely in-depth and advanced documentation that Nico wrote. I hope his website comes back because it's an invaluable source of information and it should come back. Yeah. But the step up from the official documentation to Nico is such a big step that I thought I need something in between, and I tried to provide that with the Stairway.
Yep.
So yes, if you want to know more about column store indexes, then do check that out. Absolutely. But I'm not going to talk about that today, as I mentioned.
No. Cool. No other questions.
So, filtered indexes. Filtered indexes are a very specific trick with indexes that can help performance in some very specific cases. Normally, when you create an index, the index will include entries for all the rows in the table. That's what you expect. But a filtered index only indexes a subset of all rows. And that might sound odd. Imagine you have a book on art and there is a keyword index in the back, but that keyword index only covers what is described on odd numbered pages in the book. That would be completely useless. However, if that index in the back would only include index keywords for Dutch artists, then it might be useful in some cases if you are looking for information about Dutch artists only. it would still be useless if you are looking for Swedish artists. So that is a potential benefit. In some specific cases, a filtered index can help performance because it includes only the rows you're interested in. Another benefit of a filtered index, and I'm not going to talk about that because the focus of this talk is on performance aspects of indexing, but you can sometimes use it to enforce uniqueness on a subset of rows. There are some specific use cases where a unique filtered index can be used to enforce a business rule that otherwise would have should have been can only be enforced on the business layer, the application layer. We're going to talk about performance, and the demo I am going to show is quite weird because I had to work around what was in my sample data. I didn't want to set up a more complex sample with more logic to create it. It's just a copy of AdventureWorks that I multiplied by itself multiple times to get more data. But a very realistic use case of a filtered index, probably one of the best use cases for it, is when you have a system where data that gets deleted doesn't get actually deleted from the table. It's often called soft deleted or logical deleted. In the table, you have a column named is deleted or is active or something like that, which is a bit column. And when, let's say it's called is deleted, when it's set to 1, that means that the row is logically deleted. We didn't want to lose the data. We might still need it for some historical overviews, for instance, but it should not be shown in most overviews. It should not be shown on the screen because that customer has requested not to be approached by us anymore, not to get data anymore, or it is a discontinued product or whatever. So it's not active. Because most of the queries will only show active products, a filtered index on only the active or the non-deleted products or customers or whatever can be very beneficial. It's a much smaller index, it's much more efficient, and it still includes all the rows you want. But as soon as you do a historic overview where those deleted rows are relevant as well, then that filtered index becomes completely unusable because it doesn't include all the data that might be needed for the query. So you can only create a filtered index on a non-clustered index. Again, this makes sense. A clustered index stores all the data. If we would filter the clustered index and not store a lot of the data, then we're actually deleting it because that's our only source of the data. So of course, we do not want to filter a clustered index. If you want to do that, just delete data. In the predicate of the filtered index, you cannot use computed columns, not use hierarchy, ID, spatial, or user-defined data types. The predicates that you can use are quite simple, simply equality or inequality comparisons between two columns or between a column and a value. I'm not even sure if between two columns is correct, but between a column and a value is. And you can tie them together using and or in, but not using or not. This is a weird sentence with a lot of duplicated words, but grammatically it is correct. So you cannot say an index where country is the Netherlands or country is Sweden or country is Germany, but you can say an index where country in the Netherlands, Sweden, Germany. It means the same, but one is legal syntax, the other is not. The syntax is very simple. Once more, the standard create non-clustered index syntax and then a where clause with this predicate at the end to specify which row or rows you want in the index. And this can be combined with an include syntax. So you can also add included columns in this case. Now, if you have a filtered index, then the optimizer chooses to use it or not. If the query predicate is exactly the same as the index predicate, it will usually be used. I'm saying usually. There are some weird exceptions. if the query predicate is a subset of the index predicate, then it may not be if a lookup is needed to get your correct query results. For example, let's say you have an index on last name. We're assuming a person table. You have an index on last name where country in Netherlands, Sweden, Germany. This where determines which last names are in the index. But the index data itself contains the last name and the clustered index key, nothing else, because we didn't specify an include. So if I use a query where I want only German customers, then this index can be used to find German customers. But we also find Dutch and Swedish customers, and we have to do a key lookup to find their actual country. And that cost of the lookup may make the filtered index way too expensive. And then there's also what many years ago, when I talked about this with the query optimizer team, they described as a functionality gap, where a filtered index should be the obvious choice, but something weird in the optimization process makes this go wrong. Now, in the example I just gave, including the country name would have helped. If I want only the German customers in a filtered index on last name that includes the country, then I can still, without a lookup, remove all the Dutch and Swedish customers. So this including is already a good idea, and that including also in many cases works around this functionality gap. You could also use hints, but I am usually not really in favor of using hints because they tend to backfire. They are in your code, they are useful today, but 2 years later they are still in your code and nobody checks whether they are still useful. Let's run through this query. So like I said, this is a very weird example, but I want to have a filtered index on only those people where the last name starts with R, S, T, U, or V. So larger than or equal to R and less than W. This is the where clause that I'm going to use on my filtered index called IX first name filter. The index now exists. And now I'm going to look at how many people are there with exactly this predicate. You would expect that in this case, the filtered index is used. However, what you see here is that instead, an unfiltered index, IX person name, is used. And yes, it is used with a seek, which makes it relatively efficient. But still, let's look at how much I/O this cost. This is 1108 logical reads. If I force SQL Server to use the filtered index I just created, then the number of logical reads is down to 804. So this functionality gap actually costs us roughly 300 needless logical reads. Now, if I add a filter on first name because the index itself was on first name, it is now much more interesting for SQL Server to use this index. So I have the exact same predicate as the index on the last name, but I also say I only want people named Audrey. And in this case, SQL Server will by itself determine, hey, using this filtered index sounds like a great idea here. And I only need to filter on Audrey. I do not even need to check the last name because the filter on last name in the query is an exact match of the filter on last name in the index. So every row in this index already satisfies the last name condition. No hints needed here and just 5 logical reads. However, if I do a somewhat broader first name, like starts with an A, then the functionality gap is back again. Now we see an index seek on the non-filtered index, where the seek predicate is for the last name, and the regular predicate is for the first name. This results in 1108 logical reads, whereas if SQL Server had been slightly smarter and wouldn't have had that functionality gap, it would have been just 79 logical reads. So here you see a huge performance difference because of this functionality gap. Now, it is important to know that SQL Server will not give you an execution plan that may be invalid. If I remove this hint and I say I want all orders with the last name between R and W, I will get an error. Why do I get an error here? Because I say use this filtered index. But this filtered index, let's scroll back, has all with last name less than W. The query says, that was the query, between R and W, which means W itself is included. Now, just the letter W as a last name, I'm going to assume it doesn't exist, but SQL Server never assumes. It might exist, and if Audrey W exists, then she should be included in the count for this query. Using this index, we could never find her, so with this hint, I will just get an error on this query. If it is stricter, last name between R and V, now we lose a lot of people, but everyone we need is in the index, then without a hint, we will not use the index. Or because it's Audrey. With Audrey, we will use the index because because this is very selective. So we use the index. With a more generic, like first name, like A, it would not use the index because then it would find too many people with first name A and it would have to look up the last name because the last name itself is not in the index itself. And that's where this tip, and when I create a filtered index, I basically always do this just as a generic precaution. Every column that is in the where clause should be in the index. So last name is in this case the only column in the where clause. If it's not here in the indexed columns, then I'm always going to include it. I'll create this index as well. Then I'm going to scroll back. You will see that a lot of the queries I showed are more efficient. This one still isn't. This one still uses 1108 logical reads with an index seek on the non-filtered index. We still have this functionality gap here. But these two, with a filter on Audrey, that one was already good, and with a filter on everything with an A, they are now both using an index seek on the filtered index. And you will see in the messages that they both have a severely reduced number of logical reads. Of course, more when we want more first names, but still reduced. So, questions on filtered indexes?
Not really on filtered indexes, but there's been like a discussion in the chat about the question that led to it was, can we conclude that when building an index that includes meaning, we should not focus too heavily on creating the perfect index for one specific query, but rather aim to create an efficient index that can perform better in general?
Yes, absolutely. That's basically something I'm going to briefly touch upon in the not the next, but the topic after that, finding the right indexes, and also in the over-indexing part. But you should always try to help as many queries as possible with as little indexes as possible. And that is a trade-off. And OLTP and OLAP have slightly different requirements there. But there is always the trade-off of help as many queries as possible with as little indexes as possible. And I always say the most important queries should always be helped. And the most important queries are the query that execute 10 million times per day and the query that feeds the CEO's favorite report. All other indexes, there you have to make a trade-off. And sometimes the trade-off is, yes, this query is slow, but I am not going to create an index just for this query because it would cause a lot of issues elsewhere. And this query is not important enough to pay that price. Or sometimes you have to make do with a half-assed solution that helps 10 queries a bit, without making them as fast as possible, instead of creating 10 indexes that would make each of them as fast as possible. But we'll get to the danger of too many indexes later. It's a very good discussion and a very valid conclusion. Indexed views. Before I can talk about indexed views, I need to describe what a view is. And a view is very comparable to a macro in third generation languages. So if you create a view, in this case a view with the first names of everyone where the last name starts with vis. I have no idea why anyone would do that, but it's just a basic example. If you create this view, nothing happens. SQL Server only records and saves the definition of the view. It doesn't do anything with the data. Then when you fire a query that uses this vis view, then before the optimizer starts, the parser, which is a component that runs before the optimizer, says, hey, vis view is a view. I have a definition of that view. I'm going to grab that definition and put it in the query. And then the optimizer will see this query and nothing else. The optimizer doesn't even know that a view, vis view exists. It doesn't know that you used it. The optimizer sees this code and nothing else. And the view itself was just a shorthand for your code. It is not an object in SQL Server. It doesn't affect performance. If you had typed this, you would have gotten the exact same, because this is what the optimizer gets. That changes when you create an indexed view. An indexed view is sometimes also called a persisted view. That term is more common in other database management systems. In SQL Server, indexed view is the standard term, but persisted view should be a better term, because what happens when you create an indexed view, SQL Server secretly executes select star from name of the view and stores the results. And then when data in the base table is, or any of the base tables used in the view is changed, SQL Server will automatically also update the stored data it has for that view, so that the data it has stored in the view's index is always consistent with what you would see if you just select from the view in the traditional way. Now, this is very commonly used for aggregated data. If you frequently have to report on aggregated data, then it may be very useful to store that aggregated data somewhere and then have much faster reporting, but at the cost of more work when the data is updated. So again, this is a trade-off. With data that is frequently updated and rarely reported on, I would never do this. But if the data is frequently reported on and rarely updated, then the equation changes, and it can be a great way to get better performance at an acceptable price. When you create a view that you intend to index, you can only reference tables, no other views. You need to use two-part naming, so you cannot omit the schema. For the record, you should never omit the schema anyway. You must use the schema binding keyword to prevent changes to the underlying table structures. If you use aggregation, then there must be a count big column in the select list. And there is a whole list of t-sql elements that are not allowed. And if you look at that list and think about them, then you will realize that in all of those cases, updating the view would become a big performance issue in some or all cases. All these requirements can be found in books online. Then you need to create the index, and this must be a clustered index because we want to store everything in the view. It must also be declared as a unique clustered index. And if you use aggregation, then the unique index must be on exactly the columns that you specify in the group by. No more, no less. This is the syntax, just the regular create unique clustered index syntax that you also use to create a normal clustered index. If you want to, you can after that create extra non-clustered indexes. In my entire life, or almost 30 years as a database professional, I have seen exactly one use case in a production system where it made sense to have a non-clustered index on an indexed view. So that is exceptionally rare, but if you need it, you can do it. Now, once you have that index view, you need to know whether it's used or not. And you have to realize that this view expansion that the parser does is still done. Whether a view is indexed or not, the parser will always use view expansion. So the optimizer doesn't see the view name. And yet it is smart enough to choose to use the index view using a step called index view matching. However, that step only runs on Enterprise Edition and by extension on Developer Edition. So if you have a lower edition and you still want to benefit from an index view, then you must use a hint in your query to tell the parser, do not expand this view. Leave the view unchanged in the query and pass it as a view name to the optimizer. If you do that with a non-indexed view, then the optimizer will throw an error because it now cannot create a query for you. It doesn't know what the view definition is. That was the parser's task, and you told the parser to shut up and not do its work. But if it's an indexed view, then it will be matched easily and always. So you lose flexibility. Only Enterprise Edition has the flexibility to make its own choice here. The way to override view expansion is to use the with no expand table hint. So to summarize, if you have Enterprise Edition or Developer Edition, then if you use a view with the no expand hint, the index view will always be used, whether or not it would be smart. If you use a view without the no expand hint, an indexed view without the no expand hint, then it may be used or might not, depending on which alternative is estimated to be cheaper. And if you don't use the view in your query, then the index view may still be used if the optimizer realizes, hey, I have an indexed view that can help you, even if you don't know that the view exists or that it is indexed. SQL Server is smart like that, if you are rich enough to buy Enterprise Edition. On all other editions, it's a lot simpler. If you use the no expand hint, then the index view will always be used. And in all other cases, it will not be used. Now, my demo machine uses Developer Edition, which is has the same features as Enterprise Edition, so I get this advanced index matching.
We have a question for you, Hugo, before you do the demo.
Yes.
What is the threshold to auto-update statistics on a filtered index? Is it related to a percentage of cardinality of entire table or to cardinality of
a great question, and I absolutely do not know the answer. So if the person who wants to know this can send me an email, then I can get back to them after the session if I can find the answer.
Great.
I do not know how that works. It is a great question. So in this example, I am going to just do a query where for each last name in the person's table, I want the average of the length of the email address. Again, no idea why, I just want it. And if you look at the execution plan, I'm not going to go through the details, but you will see on the right that you have a clustered index scan because there's no usable index here. And then we do aggregation, and all of this is in parallel and with sorting. And then we get the results. Now, if I create a view for this query, then it is immediately done, and there is no IO, no execution plan because nothing is done. We just stored this definition. And if I grab data from that regular view, I get results, and I get the exact same execution plan that we just saw with the exact same steps because it is effectively the exact same query. We only provided a shorthand for the developers. But now I'm going to create an index view. So I'm going to add the with schema binding. I'm going to make sure to use two part naming, and I'm going to add this count big column that is required. Now this statement is still a create view statement, so nothing happens. SQL Server stores the definition and does nothing more. Yes, this view obeys all the rules for indexed views, but it's not an indexed view. It becomes an index view when I create the index. And when I create this index, you get a very interesting execution plan. Because in this execution plan, you once more see all the steps we saw before. The same query is being executed, except that now at the end, we insert all the results in this new index that we created. And this is when, at this point, the data in this view index is completely equivalent to the data from that query, and it will remain that way. If I want to get the average, you also saw that I used the sum email length here and not the average that was here. That's because average is not allowed in an indexed view, but sum is and count is, and together we can use that to get the average by dividing them into each other. So I get the same results as we had before on all additions because I force it with the no expand hint if I use this query. And you see that it's now just a clustered index scan of this index I created on the view. And that is very efficient. It's just 7 logical reads because it's already aggregated. The amount of data is far less than the amount of data in the persons table. However, if I don't use the view and I have enterprise or developer edition, then there is this smart optimizer that also says, hey, I can do this with 7 logical reads by using that index. And of course, that same also would have happened if I used this query without the hint. And even if I use a further filter, so I say I only want the average length of emails for people with last name Kelly. Even in that case, Enterprise Edition and Developer Edition will say I can use a clustered index seek here. Seeking on last name is Kelly because the index is on last name. Finding only the row for Kelly that already has the pre-aggregated and then stored data of the view. And now it's just 2 logical reads. Without the index, the indexed view, this would say once more be a huge scan probably. Now, like I said, you can create a non-clustered index on this as well. And if you create nonsensical enough queries, then they will also be used. And the query below that will show this on other editions. But the query in this case is rather weird. However, there might be cases where it is actually useful. Okay, I'm running a bit out of time, so if there are urgent questions, do keep interrupt me. If there are non-urgent questions, I will hold them until the end so that I don't run over too much. But I do want to talk.
There is one question, but we save it to the end then.
Okay. Talking about the problem, of course, if you have so many options for indexes, clustered, non-clustered, include columns or not, which columns, filter them or not, maybe index views, the amount of options we have is huge. So how do we find the right ones? And there is no simple answer for that. You really have to understand all those indexes, how they work, what their structure is, how a seek, how a scan on them works, how they use the data in that indexes. And it has become even more complex if you also want to consider column store and memory optimized indexes. So it's a very complex topic and there is no simple way to find the right indexes. There is some guidance that SQL Server gives you in some of its dynamic management views. Those are always reset when the service restarts. So don't query them when your server has just started. Query them after a few days, weeks, or months of uptime, or on a test system after a representative test run. Also beware of long-running jobs that only run very infrequently. If you optimize indexes now in October, after the server has been up for 2 months, you will not have any traces of the indexes that are used in the end of year work. But if those indexes ensure that the end of year work ends within the nightly window we have for that work, instead of running for 4 days and making all financial bookings impossible during 4 days, then that index is still relevant, but you will not find it in those DMVs because it's only used once per year. But it's still a very important one, because you don't want the entire financial department to be blocked from work for 4 days, especially not around year end. So you can use those DMVs, but with your mind turned on. Never turn it off. The index usage stats, and I will show a sample query in the demo, has several interesting columns. The most interesting are the user scans, user seeks, and user lookups. That's the amount of times the index was used to read data. And the user updates is the amount of time the index is used to write data. Now, these counts are a bit weird because they do not have a single unit. I'll get back to that in the demo. But basically, if you keep in mind how weird they count, then if you try to compensate for that and then see that the number of reads is less than the number of writes, then it might be a bad index because we constantly keep it updated, but we don't use it that often. So that makes an index suspect. If the number of reads is larger than the number of writes, then it is not necessarily a good index, but it's probably a good index. Again, no hard statements here. There really is no simple way to do this. The second view I'm going to talk about is the missing indexes view. There, rows are added when the optimizer works on a query and thinks, hey, this index might help. And I think you're going to save this amount of estimated cost. The optimizer does not think about the cost of keeping the index updated. So if it is a frequently updated table, you should weigh in that cost. The optimizer does not think about your workload. It thinks about that query only. So it's a specialized index for that query. And the optimizer really loves the include keyword, way more than it should. So I never blindly follow this, but when I work for a client, I do look at those missing indexes hints, and I see if there are multiple hints that are all very frequently used, save a lot, and that I can combine into one single indexes or index, or maybe two indexes that then cover lots of queries. So let's first do some useless work so that we have even more data in the views. And then the first query, this one looks at the index usage stats. And if I look at the results, now the workload I did today was completely unrealistic because it's a bit weird because the creation isn't there. Normally when I run this, there's 4 lines in the results, because I also create one index before I populate the table, and then you will see 6 writes to that index, and those 6 writes correspond to these 1, 2, and then there's 4 more insert statements. And yes, one of them inserts 20,000 rows, the other inserts 640,000 rows. Both are counted as one write. And if I insert 1 row, then that's 1 more write. So that's the weirdness in how those writes are counted. You don't see it now in the demo, something went wrong. The reads also don't indicate whether it was a read that saved us a lot of performance or a read that saved us a bit of performance. So that's why we cannot just compare those numbers and be confident that they say something. But this is data that sometimes can be useful. The second query I'm going to show is for the missing indexes. And here we see that in this case, and this also, I know that this one varies. I always get either 2 or 3 indexes back. Don't know why, it's the case. I always run the exact same load, and then when I do this demo, and sometimes it's 2, sometimes it's 3, but I get them back. And this tells us on this table, create an index with this as an equality column. So this is what we should filter on. Inequality columns are probably better as included columns, but in a case like this, when there's no equality and 2 inequality columns, then you should create an index on first name first and an email length, because it's probably something like a first name is larger than something. And it recommends specifically included columns. At the end, it says the user cost of the queries was on average 42 query bucks. And this index would have saved 99.29%. On the left, there's a computed column. So this is the amount of query bucks we would have saved if all these estimates are correct. When I query this, I always order by index advantage descending, but I often also include a filter on the table to only look at one table at a time. Now, if I just create all the missing indexes, and you see I have 3 here, because sometimes this result is 3 rows and sometimes it's 2. I'm now going to create them, not because it's smart. It isn't. I say that here, it's not recommended, but because I need it for the next demo. But you should not do this. You should look at those results and be smart about it. I am not right now, deliberately. Is it okay if I go over a bit, Magnus?
Sure, no problem for me.
The last topic I want to talk about, and that's why I created those 3 useless indexes, is the risk of creating too many indexes. I have seen it on forums I have indexed every column and my performance is still bad. Yes, your performance is bad because you indexed every column. If you create too many indexes, then you hurt performance in a variety of ways. First of all, every data modification needs to be reflected in each index. Create 50 indexes, you're doing the same modification in 50 places. You increase the compilation time. Every index you add basically doubles or triples or quadruples the amount of options the optimizer has to consider. So that's a very exponential curve where the compilation time goes up. And because compilation can time out, the chance of finding the best plan goes down if you have too many indexes. Also, to make your DBA very unhappy, those extra indexes increase the size of the backup, increase the time of the backup and of the restore, which may be a problem for your recovery time objective, and increase the amount of index maintenance required, which may become a problem if your maintenance window is small. So lots of downsides to having too many indexes. I'm going to demo one of them, not the rest. But now that we have created several indexes during this talk, what I'm going to do is delete 10,000 persons. I'm going to do that within a transaction so that I can roll it back later and do it multiple times. So let's first start the transaction. Now I'm going to do this delete. And you will see that it takes a bit of time. Not a lot, but about half a second. Without the execution plan, that would be less, but it's still quite a lot of time. And if you look at the execution plan, you see why. SQL Server has to do lots of work. I'm not going to talk through everything here, but it uses a clustered index seek to find the 10,000 rows we want to delete, then deletes the data, but not just from the clustered index. It deletes it from the clustered index, but also from 1, 2 other non-clustered indexes. They are secretly hidden in this clustered index delete operator. And then it uses a table spool to store the data and then to retrieve the data multiple times to delete the data from various other indexes. Every time with a sort to optimize that deletion, but a sort isn't exactly free either. So that's a lot of work being done. And then at the end, there's even more work being done because we read the deleted data again, do some aggregation, and then join it to the clustered index on the view we created, because we have this clustered index view, this indexed view with persisted data, and we also need to update that data. So it's going to merge it, to join it, then to compute something to determine should the row be modified or deleted or inserted, do some other smart stuff, modify the clustered index on that view, and because I created a non-clustered index on that view as well, we're going to update that non-clustered index too. So huge amounts of work because we have too many indexes. Let's roll back the transaction. Now begin a new transaction, and I'm going to drop every index I created. That probably isn't smart either. The two extremes are both not very good. But I'm going to do it anyway. Now I'm going to run the same delete statement, and it simply returns instantly. And all it does is clustered index delete that immediately finds the data it has to delete in its own index. Nothing more. Like I said, this isn't smart either, but it shows you the difference that adding more indexes makes. The ideal world is somewhere in between. Leave the indexes that really help, remove the indexes that don't help, combine indexes that can be combined. Even if they then help their queries a bit less, the overall performance will be better because you have less indexes. And that's the hard part where you have to make your trade-offs. That's all I have. Sorry for going over time a bit. If you have to leave, just leave. People who want to stay around for questions, if Magnus is okay with that, I am perfectly willing to hang around a bit as well. Otherwise, mail me or tweet me and I will get back to you with my answers if I know the answer. Thanks for your attention. Thanks, Magnus, for having me. And like I said, as far as I'm concerned, we can continue with questions as long as people want to.
Thank you for coming. I had a good time. And there are a couple of questions. So the first one, I think your answer will be it depends, but we will see.
But then the follow-up question should be on what does it depend? So
yeah.
give me the question.
So the question from Gabor is clustered column store on the base table plus non-clustered indexes versus using an indexed view. Which one would perform better in aggregation on a fact table? So we're talking about data warehousing here.
You would have to compare the comparison. My experience is that a clustered column store index plus a non-clustered index, in those cases, the non-clustered index is rarely used unless it would be a covering index, because the cost of a lookup in a clustered column store index is extremely high. I don't want to push my videos too much, but one of the execution training videos actually looks at that. And I think I have a demo there with 100 million row table with a clustered column store index. And then I create a non-clustered index view, and the cutoff point where it stops using the seek plus lookup is less than 50 rows. That's how much the cost of a lookup in a cluster in a column store index is. So it can be useful in extreme cases, but in many cases it is not. So without having a chance to experiment and actually compare the performance, I'm going to say that probably the indexed view option would be the better idea.
And I think if I add my 5 cents with the column store index, if you feed the data in a sensible order to it and make use of segment elimination, then that would perform better than if you don't do that. But then
Yes,
you know
yes, but you
you
can only impose one order, and
yeah.
the demos on segment elimination are fantastic.
Mm.
But they always assume that the entire business runs just one query.
Yeah.
If you run multiple queries, you have to choose for which query or queries you want to optimize the order, and all others will not benefit from segment elimination.
True. And I think, I mean, even if you have a data warehouse with just 3 fixed reports, that's never the case, because you will have different angles on the data.
Yes, if you really have a data warehouse with just 3 fixed reports, I probably wouldn't even consider a column store index, because there are better ways for that. Just execute the reports during the maintenance window and store the results after
Yeah.
the data warehouse load. And then, of course, if your data warehouse is continuously loaded, that's not possible. And then a column store index might be the better option,
Mm.
or the indexed view. But yeah, it will be a trade-off of pros and cons against each other. And it depends on a lot of factors. Like, for instance, do you run a nightly load, or do you constantly feed new data? That is a huge factor here.
Yeah. Next question from Book is, what's your experience with compression on indexes?
I have little experience with that myself. Generally, let's say 99% of cases, if you have larger databases, compressing indexes on your large tables will give you performance benefit.
Yeah.
And that's because the time to read the data from the buffer, from the disk into the buffer pool, or the time saved by having more data in the buffer pool, is almost always more than the CPU overhead of decompressing the data. But I do not have practical experience where I was able to compare it for real customer databases.
I have done some tests with typical queries, complex queries on large tables, where, I mean, the ones where you have millions of logical reads. And as you say, if I can reduce millions of logical reads to half, then that's going to be a lot faster. So.
Yeah, most of the time the CPU is waiting for I/O to finish, so that decompression just means that the CPU waits a bit less because it's busy doing the decompression, and because it has to wait less often. But it's usually still not the bottleneck. It's usually still the I/O that's the bottleneck.
I think I've had one client call where the CPU was around 99% all the time on the SQL server, but it's rare. And
that's the exceptions.
Yeah. No more questions in the chat. There are lots of thank yous for a great presentation.
That's nice.
I agree with them all. I added one thing about the DMVs for, I mean, looking at how your indexes perform, and I added some information about if you use the tuning advisor in Azure, that's not going to consider that many weeks back in time. So if you have that, and you know you have period and reporting, don't enable the automatically drop indexes feature.
That's a good point.
Period ends. And I may add that I wouldn't do much automatic at all. I mean, look at the advices and be sensible about it.
I may be a bit, well, not a bit, I am old. I go back a long way with SQL Server. I have seen recommendations from the database tuning advisor. Since then, I have a very healthy distrust of everything that Microsoft advises based on analyzing the data and running an automated process. I do know that things have gotten lots better, and that automatic tuning is really a lot better than anything that the DTA ever did. But I am still suspect, and I would not say I would not enable it, but I would probably disable it and look at the recommendations and apply them myself if I run on a system that is new enough that the automatic indexing is supported. Or if I don't have enough time for that, or there are other reasons, I would enable it, but regularly review the views that store what the automatic indexing has done, and reconsider and think about whether I agree with what has happened.
Yeah.
I would not trust it blindly.
I know my data better than, I mean, the SQL Server can never know my data. It can know the distribution of it, but it can never understand
No,
the meaning of my data.
not your data, and also not your users. And what you
No,
just said, like a report that runs once a month and the index is unused for 3 weeks and it gets dropped.
yeah,
Yeah,
that's going to be a problem.
you need to disable that, or you need to, and I don't know exactly what you can do with automatic indexing. I'm sure there is a way to basically say pin this index and never drop it, but
I
uh,
hope.
I hope so. And otherwise, yes, just disable it, because you do not want that index dropped just before the CEO runs their favorite report.
Hmm. Alexander has a question, which is maybe I missed, but what about usage of fake column store indexes to change the execution plan to batch mode instead of row mode?
That's a very advanced topic that I absolutely did not want to cover today. As of SQL Server 2019, the use cases for that have been severely reduced, because in SQL Server 2019, Microsoft included a heuristical process to look at the data used in a query and the operators used in the execution plan to say, hey, there's no column store index here, but I'm going to run batch mode anyway.
Hmm.
Before SQL Server 2019, there were tricks, and you can find them on the internet, or you can send me an email if you want to know more. To what Alexander said, use a fake column store index, um, so that SQL Server would consider batch mode, even though all the data it actually needs is from row store indexes.